All right. Well, so that's our video, and at this point, I'm going to share my screen. I'm going to share. Essentially, I'm running Mathematica here, and I've got the notebook that I had when we filmed this originally, and so it's available to you. We can send out a link of where you can get this notebook in case you want to experiment on it yourselves. And I just want to take a couple minutes to answer any sort of general questions you had about Mathematica or the Wolfram language, anything at all. And we have our crack team of folks here at Wolfram to answer them. And then in just a couple minutes, I'll send it over to Connor. Let's see. I guess I'll just start with a question. A common question is, how do I get started? So people see this video, they think, oh, okay, cool. It looks like you can do a lot of neat stuff, but I just don't know how to get started. I downloaded the notebook. I can twirl around the little levers and stuff, but I don't know how I can how does this apply to my life? And so I guess I would encourage people to check out the Wolfram Programming Lab. So this is a website that you can go to, and there's a nice little introductory video here. And as soon as you go to, as soon as you start, the whole idea is it will teach you how to use the Wolfram language right in your web browser. And so it starts with, the most basic thing possible, 2 plus 2. Maybe I can make this a little bit bigger. You can start with the most basic thing possible, 2 plus 2. It says, oh, if you want to evaluate the cell, hold Shift and press Enter. Okay, I'll do that. And it thinks for a second, and then should spit out 4. So the idea here is that you should be able to learn the Wolfram language right from your web browser without having to buy anything, register anything. I did not have to register anything to get here. Okay, once you can do 2 plus 2, you can say, oh, well, let's try a built-in function range. And you can see that it spits out a list of numbers. And in this way, it will teach you how to use the functions of the language. There's all of these functions over here on the right, all of these other examples that you can try and learn all sorts of things. Like if you want to learn about the graphics primitives, we talked a little bit about that in the video. They have some really nice demos for how to do the graphics primitive. So they have a very low-level representation. They have a very accessible representation of how colors are represented in the Wolfram language. You can represent different colors really easily. And the next thing you know, you just scroll down here, and you can be, it'll walk you through how to do the language. Okay, so that's the answer to the question pretty much. How do I get started? How do I learn more about it? Sometimes you might be running around in here and you're curious about how to maybe label a plot. So you could say, oh, I want to know how to label a plot. And the documentation for the Wolfram language will pop up right beside your notebook here. And I love this part. This is really cool. So, okay, and you can see that. So here's the documentation. If I click on an example that they have here. So this is the plot label option to the plot command, and it makes it so that you can label your plot. And if I just go back in here and I paste it in and Shift Enter to execute it, it will make the same plot as the one in the documentation, and I can even change the name of the plot label. So right here in this website, without having to install anything, I can say haha, wow, and execute this code, and it will execute this code that I copied right out of the documentation. So that's sort of how to get started. I hope you'll check out the Wolfram Programming Lab. You don't even have to put in your name or anything if you're a privacy nut like me. I just want to go to a website and try it out. Don't want to have to give my real name or anything. That's totally available to you. All right, let's check some of the questions here. Let's see. There's some questions about finance. What can I do with financial data? And that's a good question because I have a good answer for that. I was just doing, for this class that I'm teaching, I was making some problems about the stock market. And it turns out that there is a wealth of financial data available to you through the Wolfram language. It's meticulously curated. And so, for instance, if I want to get the current value of the stock price of General Electric, I can just execute that right here. By the way, note that I'm executing these commands from within Mathematica. So here I am running Mathematica, and all of the documentation is written in Mathematica, so I can just, I can just execute these functions and get the actual real-time, this is like within the last, 12 hours or something. Anyway, so I hope that answers the question on financial data. Let's see. I could talk all day about this stuff. I really enjoy it, but I should throw it over the fence to Connor soon. I'll just maybe point out one more thing, which is people ask a lot of times about machine learning and image processing, and so I have a couple of examples. Just real quick, at one point I had a video of all these birds migrating. There were all these birds that were flying across the screen here, and I took that and imported that into Mathematica. So this is a Mathematica notebook that I exported to as a PDF. So I have this this video. I imported all of the frames of the video as a list of images, and then I could apply masks to them, multiply each image in the frame by a mask and filter out each one of the little birds, and then I could essentially apply various morphological functions to these frames. And so this is, for instance, sort of a time series of where the birds are in the video. So the vertical axis here is time, and the horizontal plane is each frame. And so each yellow stripe is a bird as it flies through the frame of the video. And so you can do all sorts of cool things with Mathematica in terms of image processing. And in the interest of time, I'll skip this. I'll just really quickly say that at one point I was running an experiment. And I wanted to read these temperature dials in a programmatic way. So I had sort of my control experiment and my control and my actual experiment. This was just for some hobby project. And long story short, I was able in Mathematica really easily to crop each frame, to unskew each frame so that I could get the digits. And then I ran a classifier function. There are built-in classifier functions that you can run. So I trained a classifier, and in essentially one line, let me see if I can find that fateful one line. Let's see. Yeah, I essentially made a classifier function that could map every one of these little digits to the digit 1 or 0 or 7 or whatever. Here it is, the classify function, and the output of which is some sort of classifier function and it will decide for you whether it should use a support vector machine or linear regression or whatever. And so based on this, I was able to, make, essentially take every picture of the temperature and map it to an actual number instead of just a picture of a number. Okay, so I think at this point I should not hog the whole time, even though I just love this and I could talk about it all day. And I want to pass it over the fence to Connor. So Connor is a PhD student, double majoring in physics and electrical engineering. He's at Michigan State University, and he's a Wolfram student ambassador. And he is going to share a little bit of his work on how he's used the Wolfram language to do simulations for his research and also just stuff for fun, too. So take it away, Connor.
Great, thank you. Yeah, as stated, my name is Connor Glosser. I'm here in East Lansing, Michigan. I have been a physics major in East Lansing for about 8 years now. And kind of day one of my physics program here, they threw Mathematica at us. And it's no small stretch to say that I kind of live and die by Mathematica now. It's worked its way into just about every aspect of everything I do on a daily basis. So what I actually work on is large, high-performance simulations of interacting quantum dots. And quantum dots aren't really relevant to what we're talking about today, but the high-performance simulations definitely are. And so that gets kind of tricky and involved. And so we spend a lot of our time playing with mathematics, trying to pull apart functions and put them together in different ways that can be evaluated more quickly, less quickly, more accurately, and so on and so forth. And Mathematica is a wonderful place to kind of experiment with all of this. It's about as close to the outright math as you can get. So one thing that I do a lot of is function interpolation. We send signals around from particle to particle, and they have to be communicated quickly and accurately. And so we have to design these very special interpolatory functions to do that. And so the easiest thing that you can do is what's called hat interpolation here, it's just linear interpolation between points, and it kind of works, but it's not really very good. So we set about trying to design this alternative set of interpolants, things that we can kind of control the knobs on and see how well they reconstruct a function. And so Mathematica was kind of my very first go-to to set all of this up, because it's so natural to try and do all of this. So up at the top here, I was able to kind of put together a function called plot basis, which is kind of designed to behave similarly to the built-in plot function. So I can kind of drag things around and label things in the same sort of way. But the idea is that I can give it a function that I want to interpolate and a set of these interpolants, and it will go through and kind of make these sorts of pretty pictures for me. And so I can kind of adjust here the number of what are called prolates that I want, and we can kind of see how the output changes. Another thing that is kind of a little bit different, so in doing these sorts of simulations of things, they're spread all across a gigantic supercomputer, and we want to kind of know where things are in relation to each other. And where we put things matters a lot for getting things done quickly and effectively. So we could just kind of throw things on there randomly, but that hardly ever works out well. So we use this thing called a Morton order Z tree. And so as I was trying to kind of wrap my brain around how this worked in 2 and 3 dimensions, which you can see is kind of non-trivial, it takes a little bit of imagination to kind of make this thing work out. I again turned right to Mathematica. And so these functions up here, coordinate to key and key to coordinates, they're the exact same functionality as you'll find in my actual simulation code that runs on a supercomputer. And they take the same data and they kind of output the same result. And I can just run it through Mathematica and wrap it in some of these nice graphics functions and see exactly what's going on. So this is laid out as a line from start, which is red, to end, which is purple. And you can kind of see the path that different things take throughout this tree. And so the idea is that things are very local. It becomes very apparent what the pattern to arrange things is here. As Justin touched on a little bit, solving differential equations is another big part of what I do. So up at the top here, I just define a couple of physical constants, the speed of light, Planck's constant, a couple of different frequencies that we use. And this is basically a representation, a model of one of these quantum dot systems that I'm interested in looking at. And so this is just one of them, and I want to see for my PhD how millions of these things interact. But to know what millions of them do, I kind of have to know what one of them does first. And so again, I turn right to Mathematica, and I just tell it to kind of solve this differential equation from time t equals 0 to time t equals whatever, and a solution just pops right out. And I can play with the different parameters, how we excite these things, the representation, what's faster, what's slower, what doesn't work, and so on and so forth. And one of the really cool things here is that the differential equation solver built into Mathematica has an enormous number of options to it. So I make use of the step monitor here to count how many steps it uses to give me the solution that I want to a prescribed accuracy. But there are also different ways of changing the type of integrator that you're using, different methods, how fine or coarse the grids it chooses are. And you can really dial this in exactly how you want for your problem. And so this step monitor thing here, for me, it lets me see exactly how much faster things go in one representation or another. And then with a solution in hand, I can run it through Fourier transform and see exactly kind of what the components are right here in Mathematica. And I can send this around to my advisors and my colleagues, and they get a really quick picture of what it is that I'm trying to do and trying to say about what I'm working on. And then kind of last but not least, I'm also involved in some graph theory, network physics problems. And so we were recently teaching some students how graphs behave, what it means to have a graph, what different types of graphs are, what the internet looks like, for instance, what social networks look like. And so Mathematica has all of this sort of analysis stuff built right into it, and it's extraordinarily easy to get to. So this website here, this connect.unikoblenz.de, they have just a bunch of network data all in kind of the same form that you can go and freely pull down. And Mathematica will happily pull it straight off the internet for you. I don't have to download it anywhere else. I can pull down this compressed file in Mathematica, and it will uncompress it and pull out the file that I want for my analysis. And then I can do some really quick calculations just to kind of figure out what the size and shape of this thing is, put it into a format that means that you have a graph, and bam, a graph pops right out of this thing. And it'll visualize it, and you can see exactly what the connections are. And then we had the students play around with some different graph theory algorithms, which, I mean, the quintessential graph theory algorithm is probably Dijkstra's shortest path. So we wanted to know the shortest path from what we called the first element in this list. Doesn't really matter what it is. And this happens to be power grid data for the United States. But we wanted them to figure out the distance in number of connections from the first element to every other element in this graph. And so there are any number of different sort of implementation details that you can look up online, but it's really pretty straightforward to implement in Mathematica. You just create a couple of arrays to hold some data for you, and then you just basically compute where you're going, get rid of where you've been, and then fill up these arrays with the appropriate data. And then built right in here is the find shortest path algorithm or function. So students can take their own solution and compare it with the built-in solution, and you can see that they get exactly the same thing. There's no difference in these two implementations. So it really kind of decreases the barrier to entry for a lot of this mathematical science work. You can really dig in, and they call this a notebook, and it very much is. I essentially doodle with code to kind of put a solution together and imagine how it works. So that's all I had to say about what I use it for. I'll just kind of scan the chat here real quick to see if there are any questions that anybody sent my way. It doesn't really look like it. So in the list plot function, you can join the points using joined true. Is there an easy way to join them somewhat more smoothly than just line from point to point? That's a really great question, and it's something that I run into very frequently. So let me just pull in a new notebook here, generate some random data. That is random real from -3 to 3, and I'll take 16 data points. So I get 16 random numbers, list plot that, and they're kind of scattered from -3 to 3 appropriately. One of the best ways to kind of smooth this out that's built right in is the interpolation function. So we say my func is equal to interpolation of dat. And this essentially returns some function object that behaves just like a mathematical function that we all kind of know and love. And then you can plot this just as you would with the regular plot command. So plot my fun of x from 1 to 16. And all of these points get joined up and in nice, smooth interpolation. And you can control the order of the interpolation, the different type. And so if you show the plot and the list plot of that, you can see that they're right on top of each other, and things have been smoothed out kind of nicely. Any more questions?
In the interest of staying on time, I might just ask that Connor can answer those while I'm launching into the next thing, if that's okay.
Absolutely, I would be happy to pass it back your way, Justin.
Cool. All right. Thanks, Connor. That was really cool. And yeah, feel free to continue launching your questions to Connor. And at this point, I'm going to share my screen, and I'll just say just a quick word on hackathons because I'm actually going to a hackathon this weekend, and I'm really looking forward to it. And I expect that some of you folks in the audience have done hackathons before, and I just want to sort of make the link between how could you use the Wolfram language or Mathematica in order to how could you leverage that at a hackathon. Okay, and the other thing I should mention, let's see, we had a lot of questions in the Q&A about the difference between the Wolfram language and Mathematica, and I just touched on it in the video real quick, but essentially the difference is that the Wolfram language is the programming language that powers Mathematica. So Mathematica is a desktop program. There's also an online version, so it can be confusing. But originally, Mathematica was a desktop program, and it had a lot of very powerful industrial strength algorithms under the hood for doing symbolic computation and all sorts of other computation. And that kernel, that computational kernel that powered Mathematica, the folks at Wolfram realized could power lots of other things. Like, for instance, Wolfram Alpha is a web page, and you essentially enter in natural language queries, and it goes to essentially the Wolfram language kernel that can answer your queries. And so, for instance, the Wolfram Programming Lab, which I was showing you earlier, this business here, this is a web page where you're doing things that are executing the Wolfram language code, and it's being executed on Wolfram language servers that are running that kernel. So that's the difference. The Wolfram language is a programming language, and Mathematica is just one program that leverages that programming language. Okay, so back to hackathons. There are a bunch of sort of use cases here where folks have won hackathons that by using the Wolfram language. And one of the reasons that it's that you can do this is there's so much data available built into the Wolfram language. It's unlike any other sort of normal programming language because there's also a huge library of curated data sets available for you. And so here's an example of one of the winning entries, which was somebody brought in a bunch of financial time series data, and then through the Wolfram language, they didn't even have to download any text files or anything. You can just bring it right in. I'm sorry, this is maybe yeah, I guess this is financial time series data, and then they could cluster that data using like graph theory, graph drawing algorithms that's also built into the Wolfram language. Here's another example where somebody has written an app on their smartphone for taking a picture and then breaking that picture down into sort of components like you would have if somebody was teaching you to draw. First draw the circle, then draw the legs, and blah blah blah. And they were able to power this with Mathematica and with the Wolfram language. So anyway, there's just a couple of examples. In the interest of time, I should probably stop talking about hackathons, but I think they're really cool. I'm really excited for the one this weekend, and I definitely encourage you to visit this website that I'll post publicly here in the chat window if you want to know anything more about it. So let's see. At this point, I guess I think we're at good shape time-wise, and maybe I would just thank everyone for coming. We still have a lot of people hanging out, and if you want to continue to talk, we have there'll be a little chat session afterward. After we close the Adobe Connect session, there'll still be a little chat icon at the top of the window, and that is just a giant chat room where we can answer any remaining questions. And thanks everyone for coming. I really appreciate it. I hope we were able to answer all your questions. Yeah, I look forward to resuming further discussions in the chat window. Let's see. Thanks very much for coming, and I hope to talk to you soon.